Hello and welcome to this lab session on training quantum circuits in the Qiskit Global Summer School on machine learning. My name is Julien. I'm a pre-doctoral researcher at IBM and EPFL in Lausanne, Switzerland, and I'm mainly working on near-term computing and quantum algorithms. And I'm thrilled to give to you today this lecture. Well, not exactly a lecture, more a hands-on lab. You'll have this notebook available that you can play with and hopefully also the exercises. And yeah, without further ado, let's get started. So today we'll talk about training quantum circuits, in particular training parameterized quantum circuits, because of course we need something to train. And while the summer school is mainly focusing on machine learning, the technique of training parameterized quantum circuits is very widely applicable, in particular in this setting of near-term computing, because on near-term devices, the most algorithms that we're looking at are variational. That means that they include some sort of feedback loop where we train parameters. And just as a quick overview to get started, here you can see I picked three different near-term algorithms that all have the same structure, and what you learn here today you can apply to all of these three algorithms. So in top left corner you see the VQE, or the Variational Quantum Eigensolver algorithm, that you probably already have seen in a previous lab session with Johannes. So in the VQE we have a physical Hamiltonian that encodes the energy of our system, and we have an ansatz wave function that is used to model the wave function of the system. This ansatz wave function, called psi of theta, is usually prepared by a circuit with initial state 0, so all the qubits start out in state 0, and then we apply a unitary that's parameterized. So this U is some circuit that has gates in it, and these gates are parameterized, and that's where these thetas are coming from. And since this is a physical Hamiltonian, we need to transform the qubits into the proper basis before we measure that, and then we can combine the measurements for the expectation value, and this expectation value is then what we want to optimize. Very similarly, we have QoA that you already definitely have seen with Johannes' lab, which has the very same structure. However, the Hamiltonian now is diagonal because it comes from a classical optimization problem, and the ansatz has a very particular structure. Namely, there's the structure of the QoA ansatz, which depends actually on the Hamiltonian. But again, it has the same structure. It has this expectation value that's parameterized that we want to optimize, and these parameters that we want to optimize are part of the circuit. Then, more in the machine learning spirit, we have the variational quantum classifier, or VQC, which you can think of as a minimal model of what people call a quantum neural network, because it only has one layer of data encoding and one layer of a trainable model. And in general, this is a combination of many expectation values, but in the end, this also is just a parameterized quantum circuit, and maybe you have multiple of them and you have to train all of them. But all of these which are examples from chemistry, from optimization, from machine learning, they have the same feedback loop in common, which you can see here at the bottom, where we have here on the left side a classical optimization routine, which updates parameters theta to theta n plus 1, plug that into the expectation value. So this will be plugged into our quantum circuit that runs on a quantum device. The quantum device is used to evaluate the expectation value, and then that's sent back to the classical optimizer. And then we loop until we reach some maximal iterations or reach some termination criterion. So all of these are essentially training quantum circuits, because we train the parameters that are inside of the gates in a quantum circuit. And we'll start off with examples that look more like the VQE or QoA, but they are applicable also to QNNs in general or to VQCs. And in the end of this lab session, we'll apply them to the VQC. So the task in general that we're looking at is that we have some loss function f that depends on some parameters theta, and we want to minimize these. We want to find the optimal parameters theta star so that this expression f of theta becomes a minimal. Just to recap, f of theta, for instance, for the VQE and for the QA are these expectation values, so nothing magical happening here. And for the VQC, it's a combination of expectation values. So this L is some loss function, some combination of multiple expectation values. And now how do you, so ignore, for instance, for now you can ignore the quantum setting. How would you minimize a loss function, or how would you minimize this function f? So a very, very widely used and very efficient strategy to minimize a function value is based on gradients. So if you have this function f that's here sketched in blue, and you have access to the gradient of the function f, so this is this nabla of f, and you have an initial point called theta 0, then a very obvious technique to minimize this function value is to just walk down the steepest gradient of f, right? So assume you would start here and you know that the function goes down in this direction, then you would just follow this direction. And naturally, you would, after some steps, you wouldn't end up in the minimum. This technique is called the gradient descent, or sometimes vanilla gradient descent technique. Vanilla because it's the plain gradient, you don't do anything special to it. And the update rule you can see in this red box here on the top right, where we say the next parameter, theta n plus 1, is the current parameter, minus the gradient times some learning rate. And this learning rate is just a scalar factor. It's positive and a small scalar factor that makes sure that we don't take too large steps. So assume you would start here at the top and your learning rate would be very, very large, and then maybe you would jump out very far, which you don't want. So usually to faithfully go along the line of the function, you choose a small learning rate. Like that depends on the exact problem at hand. But usually people choose something like 0.01. Right. So let's set this into a quantum setting. So as said before, usually this ansatz wave function is prepared by some unitary or some circuit U that depends on parameters theta. And here, let's really concretely fix it. And we'll use a circuit from Qiskit circuit library called the real amplitude circuit. We'll use it on 2 qubits with only 1 repetition and a linear entanglement. And when we draw it, you can see that the circuit that we're using for our ansatz looks like this. So we have these RY gates. They are parameterized because you can see these little thetas here at the underneath the RY, and it only has 1 C0 entanglement between these 2 qubits. Then our Hamiltonian is going to be a very simple classical Hamiltonian with just 2 Z operators on both qubits. Right. So this is a very simple example, and let's have a look at how we can minimize that. So first of all, we need to be able to evaluate this expectation value. In math, on paper, you would write the expectation value as you can see here on top. So the bra of the state times operator times the ket of the state. But of course, that's not something that you would, that's not what happens on the hardware, and it's also not what you would do in Qiskit. So to evaluate this expression in Qiskit, we can use the opflow module again and import a state function, and then we can write this expectation expression as a state function of the Hamiltonian and say that this is a measurement. So this expression here says that we want to measure something against our Hamiltonian, and the state that we want to measure is this ansatz. So we say state function of the ansatz, and that gives us a object that we can evaluate, and that gives us the expectation value. So to look now at different techniques on how you could calculate the gradient, let's fix some point P. So we fix some value for our parameters and fix an index. And then we have a concrete problem which says, given this point P and some index I, what is the gradient of the expectation value for parameter theta I and evaluate it at the point P. And if we can do that, if we can do that for all the dimensions, for all the parameters theta 0 to how many parameters we have, then we can calculate the gradient, and then we can do gradient descent and find the minimum of our loss function. Right, so here we'll choose, since we actually do the calculations, let's also choose a random point. We'll just select, use NumPy to choose a random point. And the index that we'll be using is the index number 2. So that's the top right RY rotation gate. Right. To execute all the circuits in this lab session, we'll use a shot-based simulator. So this simulates the shot noise of the quantum circuit with 8,192 shots. This does not include any noise from decoherence or any other noise, just shot noise. Right. So let's talk about how we can calculate these gradients. The simplest technique to calculate gradients of actually any function is using a finite difference scheme. A finite difference scheme is quite simple. Say you are interested in the gradient of f at this point theta here. Then what you can do to estimate the gradient, just by the definition of the gradient, is you can choose some small distance epsilon, go a little bit into one direction, go epsilon far into one direction, go minus epsilon far in the opposite direction, and then take the difference of these two function values divided by the distance, which you can see here. And that will give you an approximation for the gradient at that point, which is just the tangent at that point. This works especially well if you have a function that is very smooth, so you don't have any noise in there. And if you have functions that don't oscillate a lot. So here in this example that I've drawn on the slide, that would work very well. So how can we do that in Qiskit? In Qiskit, first of all, we would have to write a function to evaluate these expectation values, because that will just make our life generally easier. There's an exercise about that. If you don't remember how to evaluate expectation values, that I encourage you to do. But here I've just recapped everything. So to evaluate expectation values on a quantum computer, you will have to convert the Hamiltonian into a Pauli basis so you can measure it. That's what this expectation value converter here does. So we'll say Pauli expectation dot convert the expectation value. And then we need something to evaluate the circuits. And that's what the circuit sampler does for us. And we'll just plug in the quantum instance that we defined before using this Quasum simulator and 8,000 shots into the circuit sampler. And then when we have parameters x, so this is an array of function values, we can map that to the ansatz parameters. And then we can tell this circuit sampler to convert we can tell this circuit sampler to evaluate our expectation value that's in the correct basis, given the parameters. And then we click eval, that evaluates the circuits. And since we know that our result is real, we just ensure that everything is real. So this is really just a function that, given some numerical values for my parameters, that will evaluate the expectation value. Right, and now let's just apply the finite difference rule. So we'll use a epsilon of 0.2, which is not that small. And we'll use the identity vector. Since we have a vector of parameters, we'll have to pick out the dimension that we want to perturb in. So this just gives us the identity vector with a 1 at the index. For the index, for us it's 2, and otherwise 0. Then the perturb parameters are point that we evaluate at plus epsilon times the identity vector at minus epsilon. And now we can just evaluate that. So now we can just say evaluate the expectation at plus, evaluate the expectation at minus, and divide by a difference. And if we plot that, then we get the gradient of minus 0.5. And that's it. You can also do that with Qiskit. You don't have to do that yourself if you use the gradient object. So the gradient object is, or the the entire gradient framework in Qiskit Opflow allows you to calculate gradients for different expectation values and circuits, and use different techniques to do that. And to do finite difference gradients, you can call this gradient object and say you want finite difference gradients. So it's not analytic gradients, finite difference, and with a given epsilon, you want the gradient of the expectation object that we defined beforehand, and you want it at that particular index here. And now when you print that, what you get back out the gradient, then you can see what circuits are actually evaluated by Qiskit. And you can see that it's some coefficient. So this coefficient 2.5 is 1 over 2 epsilon. And the expectation value of the ZZ operator times these two circuits. And now you can see that these circuits have the parameters of that we defined. But the second parameter, theta2, is shifted by 0.2 plus 1 time and minus 1 time. And when you click eval now and you bind parameters to it, then you can see that we again get about minus 0.5. So note that these results differ because we use a shot-based readout. So if we would use a state vector simulation, then this would be exactly the same as we did before with the manual finite differences. So finite differences are great because you don't have to care too much about the internal structure of your function, but they can be dangerous. So imagine you have a noisy loss function, which is exactly the setting that we have with quantum computers, and you only have a noisy access to your loss function. So instead of this smooth thing that we have before, we now have this wavy approximation of our function. And assume you happen to choose a small epsilon that is just unlucky in a sense, and you evaluate the gradient at this point here. So the true gradient that we also have seen before would go down on the right direction. But due to the noise, it could happen that you evaluate on the right side at a function value that is too high, on the left on function value that's too low, and then the finite difference gradient that you estimate goes to the left, and you'd end up going into the wrong direction. So we can prevent that by not using finite difference gradients, but instead use analytic gradients. So analytic gradients don't use an approximation like finite difference. They try to evaluate the analytic formula for the gradients. In general, that's not too easy because you would have to do a manual calculation. But for circuit-based gradient, for expectation values based on circuits, there's a very nice theoretical results, which gives us a very easy formula for evaluating gradients. If you want to know more about that, then you can look at this paper I've linked here. But in a simplified manner, if you have a circuit that consists only of Pauli rotations without any coefficients, then this rule tells you that the analytic gradient looks very similar to the finite difference gradients. In particular, you can, instead of perturbing with some random epsilon that's very small, you have to choose an epsilon which is pi over 2, and then divide not by the distance, which would be pi, but divide by 2. And this rule will give you the exact analytic gradient. And this is very widely used actually. And if we implement that by hand, then we just have to reuse the same code as before, but now we choose an epsilon of pi over 2, and now we divide by 2 here. The rest is the same. And you see that the value is actually quite similar to what we had before, but it's not quite the same. So it's minus 0.2552. Of course, you can again do the same thing with Qiskit and just use the gradient converter again. So the parameter shift rule is the default if you don't specify anything. And you see that now this is actually very close to also our finite difference. So you see that it's in a sense it's more accurate. Right. So now we know how to calculate gradients, both by hand and with Qiskit. Now let's try optimizing some function. So the function that we look at is still the ansatz with the real amplitudes circuit and the ZZ Hamiltonian. This is 4 parameters. So now let's choose some random initial point. I fixed it here for reproducibility. And now we can optimize that. So we have a function already that optimizes that evaluates the expectation value. But if we want to do gradient descent, then it will help a lot if we have a function that can evaluate not just the expectation value, but also the gradient of the expectation value. And I've written a function for that here. It's very similar to the evaluate expectation as before. However, there's one difference, namely that we add the gradient calculation in here in the top. And this function now evaluates the gradient given some parameters x. All right, so to keep track of how our loss function changes, and so in a sense to see how good our optimizers are, we would like to keep track of the loss at every step. To do that, we can use something that's called a callback. So if you remember the structure that we had before with the classical optimization routine here on the left and the evaluation on the quantum computer on the right, and where it iterates, so you give the parameters to the quantum computer and you receive back the function value, you can add a callback which acts as a kind of hook on this classical side and which in each step sends you back some information. Concretely, if you want to implement that with one of our optimizers, so here we'll pick a gradient descent optimizer that's implemented in Qiskit algorithms.optimizers. We can define a callback function that receives the number of function evaluations done so far, the current optimal parameters, the current function value, and the step size of the gradient. Since we just care about the loss, let's just store the function value. In general, our optimizer here will do 300 steps and will choose a learning rate. This was the small eta from before of 0.01. And yeah, now that we have all of that, we can call the optimizer that we call GD and call its optimize method with the number of parameters, the function that we want to minimize, the gradient function that we want to use. We'll use the parameter shift rule and the initial point. And when we have that, we can plot the loss. So here we have just a plot that essentially plots here the loss that we stored with the callback. And we can see that we start here at a function value of around 0.9 maybe. And the gradient descent very nicely walks down the function value and reaches the optimal value at around 250 iterations. Great. So if that's so easy, why do we have this lab session at all? So of course it's not that easy. No, it's not that easy. Because gradient descent does not always work that well. So assume you have a very nice loss function. So as you have here on the left, you have the steps eta are rather small compared to the landscape. And you can start here at the top and nicely walk down a smooth line down to the minimum here. But now imagine that you don't know that much about your loss function and the landscape in which it lives. Say, for instance, it's squished in the x dimension by some very large factor. Then it could happen that you start here and the learning rate is way too large. And instead of walking nicely down to the minimum, as you can see on the left, you will overshoot. So you'll jump way too far, and maybe you'll end up oscillating and you will never reach the minimum. So this is the problem of the vanilla gradient descent optimizer. Luckily, there's a nice resolution to that based on what's called the quantum Fisher information and natural gradients. And to understand the resolution to that, let's ask the question, given two parameter vectors, θ1 and θ2, marked here in orange, how far are they from one another? And a very obvious answer to this question is, I have coordinates or parameter values of the one parameter, I have parameter values for the other one. Well, distance, also here in the normal space, the distance between you and me is just the Euclidean distance. So I'm just going to take the Euclidean distance of these two parameters. And in everyday life, that might be a good choice. But if you have a model underlying these parameters, then it's not really. Because assume you have the same model as before on the left, which is very nice, and you have these two parameters that will be plugged into the model, then it seems that the distance in this model here should be different than the distance in this model here on the right side. Because my model at the point θ1 on the left side doesn't change that much to the point theta 2. But on the right side in model B, changing my parameters a little bit in the x direction will change my function value a large amount. So the idea of the natural gradients is that we change the way that we interpret the distance. Instead of having a distance measure which is independent of our model, we'll have a distance measure that is dependent of our model. And we'll say that we'll interpret the distance between the parameters theta 1 and theta 2 by the fidelity of the ansatz given these two parameters. That's given here by this formula on the right. And this induces a metric called G, and we'll see that in a second. And this now gives us a distance that depends on the model. That gives us a sensitivity feeling. So if my model changes very much for a small change in parameters, I can see that now, which before I couldn't. So this metric G that this distance induces is called the quantum Fisher information. And that is the quantum version of the very well-known Fisher information in classical information processing. And you can work on the formula for that, which looks like this. We don't care about it too much. Qiskit will take care of that for us. And now we can update our gradient descent rule by using this information of the metric. And the way that this looks like is written here in this green box. And that update rule is known as the quantum natural gradient descent. And the only thing that changes to the vanilla gradient descent is that before updating our step with the gradient, we multiply the gradient with this matrix, the inverse of this matrix G. So this is a matrix inverse here. If you want to read more about that, you can have a look at this paper I linked here. Now, how does it look in practice? So this model, this quantum natural gradient is invariant under parameter rescaling. Fancy words. In practice, that means that if I squish my model into one direction or another direction, the update steps will not be affected by that. Meaning that when I have in my simple model this nice smooth line, I will have exactly the same line in my rescaled model because it scales with the size of the model in the end. And what do you have to do to use that in Qiskit? It's very easy. All you have to do is you have to change wherever you put gradient by natural gradient. So this is also a class in Qiskit.opflow. So now to do optimization with that, let's write a function to evaluate the natural gradients, similar to what we had before. So now again, you see that we define the expectation value here. Instead of the gradient, now we have the natural gradient. Here we're using a regularization. It's not very important conceptually, but for those who are interested, since we take the inverse of the quantum Fisher information, or we have to solve a linear system of equations, that can sometimes be unstable if you have a shot-based readout or if you have noise. So this adds some regularization to the solution of the linear system and gives us a more stable update. Then again, we do the conversion into polybases, define the circuit sampler, and evaluate the natural gradient. And now if we evaluate the gradient and the natural gradient at some point, we can actually see that it's different. So these gradients, these update steps will give us a different path in our loss landscape. So let's try to optimize and see how that works. Again, we'll use a callback to keep track of the loss. And we'll use the same learning rate as before, so that it doesn't have any advantage. And if we optimize and plot the loss, then we can see here that the quantum natural gradient, the green line, effectively trains faster than the vanilla gradient descent and reaches the minimum already at around 170 iterations. And there are many benchmarks in literature in that, and in general, the natural gradient descent seems to converge faster. And it's also more stable because you don't have to calibrate the learning rate that carefully. On top, for people interested in theory, there's also a nice connection of the natural gradients to quantum imaginary time evolution, which you can use to show that if you have a non-zero overlap with the ground state, so the initial state is somewhat related to the ground state, then you have a convergence guarantee. So if you have if you're sufficiently close, you can prove that you will reach the optimal solution. Right. So now you could also say, is that it? Now we have the magic formula. Now we've solved the problem. Not really, because if you try to evaluate this natural gradient, you can see that, or you've seen that you need to use this matrix G beforehand. And that can be very expensive to evaluate because that's a matrix and generally needs a quadratic number of evaluations. And we can plot the number of circuits that we need, or number of expectation values we need to evaluate for a gradient and for natural gradient. And we can see that the vanilla gradient scales linearly in the number of parameters because you have to compute every parameter derivation individually. And the natural gradient scales quadratically because you have to evaluate this matrix G. And if the number of parameters grows and is not just 4 as we have in our example, but maybe it's 1,000 or tens of thousands of parameters, then the number of circuits we need to evaluate explodes. And especially with the near-term devices, that's not something that's feasible. So what do? Luckily, classical literature also has the same problem. If you have many parameters, then evaluating gradients just is expensive. So what people started to do is a stochastic approximation of your gradient. So if you remember if you remember how the gradient is calculated, for instance, in the finite difference scheme, then you can look at your gradient of the function f as the vector that it is. So you have a derivation in each parameter dimension. And if you would define difference, then you would perturb every single parameter dimension individually. So you would first go ahead and perturb parameter 1, then 2, and so on until n. And here you can clearly see that you need 2n function evaluations to get the gradient. And that's linear in the number of parameters. So what you could do instead is you could say, I don't actually care about the exact value of the gradient. I just want to reach the minimum. So if you give me something that gives me an approximation to the gradient, but is much cheaper, then I can also work with that. And that's exactly what the simultaneous perturbation stochastic approximation, or SPSA for short, does. It picks a random direction. There's some restrictions on that, but if you choose, for instance, a vector with plus minus ones randomly, then you're good. And then you choose a small epsilon, and you do a finite difference approximation just in this one dimension. So you pick this random dimension, you go a little bit epsilon step into the direction, you go an epsilon step back, and you say, okay, this is now my gradient. And you multiply that with the component-wise inverse of the perturbation. So you can see that whereas here you have 2n function evaluations, here you have only 2 function evaluations, and you multiply that with a vector. Now that's not a particularly good approximation of your gradient, but you can show that that's an unbiased approximation of your gradient. And that means that on average, you will approximate a gradient. And in practice, how this optimization usually looks like is that where the exact gradient has a very nice and smooth line that leads to minimum, the SPSA kind of jumps left and right of it because of these random directions that are chosen. But you can show that it converges under the same boundary conditions as the gradient, under the same conditions as the gradient. And this is a very cheap alternative that also works very well in practice. So Qiskit supports that with the SPSA optimizer. So we'll do the same thing as before. We'll try to see how the loss of that SPSA optimizer develops. We'll define a callback for that. We'll use this SPSA optimizer. So again, with the same learning rate. So it's a fair comparison. And now also we have to specify this perturbation, this epsilon, which we'll set to 0.01. Note that here we'll not need any gradient, since the gradient is approximated with the kind of finite difference approximation. And if we now plot the loss, I fit in the code because it's is repeating the same thing again and again. If we now plot the loss, then you can see that the SPSA really almost exactly coincides with the vanilla gradient descent. And just at the fraction of the cost, because instead of these linear dependence in the number of parameters, SPSA has a constant cost in the number of parameters. It also works really well and finds a minimum at about the same number of iterations. So that's already great. But now you might ask, okay, I've learned about natural gradients, and I've learned that they are better than or in general seem to work better than the gradients. Can I use this SPSA kind of technique also for natural gradients? And the answer is yes, you can. I'm not going to talk about details here, but in general, the idea is that you can rewrite this matrix G. That's this formula that you've encountered before already. You can rewrite that as a Hessian of the fidelity. So it's like a second derivative of this fidelity here. And you know that SPSA works for gradients by using one random direction delta. And then you can generalize that for instead of a gradient with one perturbation, you can generalize that for a Hessian with two perturbations. And then you can combine steps 1 and 2, because here you have a Hessian and here you have an approximation of a Hessian. You can combine that, and then you can use SPSA to approximate this matrix G. And with that, you can use this Hessian approximation and the gradient approximation and combine that to a natural gradient. Details are again in a paper if you're interested into that. So Qiskit implements that as the QN SPSA optimizer. That stands for quantum natural SPSA. And again, we can compare the losses. So we can here define again a callback. We'll store the number of, we'll store the loss here. The signature of the QN SPSA is a bit different because you need to know the fidelity beforehand. But in the end, it also uses a learning rate and a perturbation. And if we now look at how that trains, then we can see here in the dashed green line, the QN SPSA optimizer, which seems to be kind of close to the quantum natural gradient. So I know that in this particular example, it looks like it would be better, but that's just because of noise. If you do that many, many times, then you can see that the QN SPSA is actually very close to the quantum natural gradient. And this is together is a great result, because now we have seen that a gradient descent is a very successful technique and it works. That's a solid blue line here. We have seen that natural gradients are more stable than gradients and give us some convergence guarantees, and they also converge faster. So this is the solid green line. But we've seen that they are expensive to evaluate. And we can counter that with stochastic approximations, that even though that they are approximations, since they are unbiased, they evaluate the quantity that we want to look at very well. And these are these dashed lines, once for the gradient and once for the natural gradient. Right. And if we now look at the costs, then here again you see the costs for natural gradient and vanilla gradient, which are quadratic and linear respectively. And the costs for SPSA and QN SPSA are constant. They don't change, they're independent of the number of parameters, because you only choose these random directions. And here's a small offset between the natural SPSA and SPSA, because natural SPSA needs more evaluations for the approximation of this matrix G. Okay, so far so good. However, this is a lab. It's not a pure theory session. So I want also to give you the information of what happens in practice. And in practice, especially since circuit evaluations are very expensive, people tend to use these SPSA optimizers over the gradient descent optimizers, just because it's cheaper and it's much faster. And instead of using a fixed learning rate, people actually use a exponentially decreasing learning rate, which is large in the beginning and then becomes smaller. So here you can see two plots. On the bottom, you see the learning rate, eta, which for SPSA starts at some large value and then exponentially decreases and goes more down and down and down. And you can here see that the dashed line is the constant learning rate that we've used before. And with the constant learning rate, the convergence that we've seen is here, this dashed line on top, which is kind of very smoothly and continuously going down. However, if you now exchange this constant learning rate for this exponentially decreasing learning rate, what you find is usually a convergence which looks more like a step or like a very steep mountain, where in the beginning, since you have a large learning rate, you converge to the minimum much faster, and as the learning rate gets smaller, you find more finely optimize the loss function value, and this works well if you know how the loss function looks like. So if you can start with if you know how sensitive your loss function is, then you can calibrate this learning rate so that this works very well and that you don't overshoot. But if you don't know much about the loss function, then that can still fail. But in practice, we know a lot about the loss functions, especially because the sizes that we look at right now, we can still reasonably simulate on a classical computer. And thus, in many practical papers, people use this SPSA optimizer with this exponentially decreasing learning rate. If you look into Qiskit, then and you don't specify the learning rate for the SPSA optimizer, it will automatically use this exponentially decreasing learning rate and automatically do some kind of calibration. And if we plot that, then here we can see that it works actually the best. Again, this is it's a very small example that we're looking at, and for larger examples, then this power law SPSA will not work as well, but will probably be more like the natural gradient or a bit worse. All right, so now you've seen different techniques on how to minimize loss functions that are very simple. So we minimize just a single expectation value. But after all, this is a machine learning summer school. So let's apply that to to the two QNNs, or in this case, a variational quantum classifier. So just a QNN with one feature map and one variational circuit. So just to recap, the structure of a VQC is the following here on top. So the circuits have a feature map that encode the data. These feature maps usually use these diagonal P gates. So a P gate is a phase gate that has a 1 on the top right corner and a exponential in the bottom right corner, top left and bottom right. And these controlled phase gates, and where phi is some function of the two inputs. And you have a variational circuit which is used to train, and here we'll again use the RY amplitude, real amplitudes ansatz that you've seen before. If you have some label data, then you evaluate the circuit for each of these data points x and your current parameter values theta. You do some parity measurements, for instance, with the global Z operator, as you can see here. And then that result gives you is interpreted as a label. If the label is correct, so if this label output here on the right is the same as y on the left, then you're good. And otherwise, you have to update your parameters. So we'll to use a complete example, we'll generate some data with Qiskit's machine learning package. So you have this ad hoc data which you can use, which generates you some data. So we'll use 20 training features, 10 test features in 2 dimensions. And we can plot that. And here you can see the data. So the filled circles are the training data with class A in green and class B in blue. And the hollow squares are the test features that we want to classify. To build a variational quantum classifier, we need the feature map, the ansatz, and the observable, like in the doodle that you've seen before. So for the feature map, we'll use the ZZ feature map from the Qiskit circuit library. This is just the same feature map that I've drawn. And again, the real amplitudes ansatz. Again, with only 4 parameters, so it's easy to train. And if we plug that together into a circuit that looks like that, so first the feature map and then the ansatz, and the Hamiltonian that we'll use is again a global Z operator. Now that we have all the constituents, we can use a Qiskit, we'll use the vanilla gradient descent again to optimize that. We'll use 100 iterations and a learning rate of 0.01, and keep track of the loss. And now we have all of that defined. We can define our QNN with Qiskit machine learning. We'll use the opflow QNN. That's because we have we will do these measurements with the Z operators in the end. The full expectation value that we want to evaluate is the Hamiltonian, the ZZ Hamiltonian, times our circuit. So the circuit contains the feature map and the variational circuit. And we'll plug it into the opflow QNN object with saying that we want to evaluate that expectation value, giving a list of the input parameters. So this is what the data will be, where the data will be plugged into, and what are our weights. So this is what we train. We want to use a Pauli expectation value because we want to simulate what happens on real hardware. And we'll do vanilla gradient descent. So we need to specify what kind of gradient we want to use. And of course, the simulator. Now we've defined our QNN unit. Then we can define the classifier. So the classifier is a neural network classifier from Qiskit machine learning algorithms, and it takes the QNN that we just defined, the optimizer, and for reproducibility, we'll plug in some initial point that is randomly chosen. And once we have that, we can fit our data. So we'll call classifier.fit with the training features and the training labels. And then to predict, so that takes a while. I've run that before for you. And then we can predict the labels for our test features, and we can plot. And now you can see that these squares are filled. They're filled in green for class, if we predicted class A, and in blue if we predicted class B. And for all the labels that are wrongly classified, I've drawn a red circle around it. And you can see that here, out of the 10 test features that we had, we only classified one wrongly, which is an accuracy of 90%, which is not too bad. Of course, that's a very small training set of only 20 training points. All right, so now that we've seen how to optimize with a gradient descent optimizer, now we can look at how that would look like with a natural gradient, because we've seen before that it works better. Hopefully it also works better for the VQC. So all we have to do for that is, again, define a callback and our optimizer. And now instead of passing in the gradient object as a gradient, we'll pass in the natural gradient, specifying some regularization that we want to use. And then again, we can define a classifier with this new QNN object and the initial point, fit, and predict our data. So here we actually didn't predict, but we just optimized because we're interested in the loss. And if we now plot the loss for these both optimization techniques, then we can see that firstly both seem to find the same minimum, which is and do some optimization. But even though they both seem to work really well, and vanilla gradient descent finds the minimum really quickly, natural gradient descent is still faster than that. So the optimization here took longer, but you can see that it works really well for both cases. So to speed up that, you could, of course, use the SPSA optimizers, but I'll leave that as an exercise to the motivated listener. Great. So now we have seen different ways to optimize different kinds of loss functions. We've looked at the simple loss functions for VQE and QA, and we've looked at a more elaborate example that for the VQC that is generalizable to all types of QNNs that you have seen today in the lecture. But now we want to talk about limits in training quantum circuits, which you've also seen in the lecture beforehand. So the main problem of variational circuits that we have right now is that the gradients of our circuits vanish. This is called Barren plateaus, and there are two very good papers on that you can read. And what that means exactly, we'll show you in a second. And the the model at which we will investigate that is our favorite ansatz, the real amplitudes ansatz. Only now we'll scale it to much larger sizes. So we'll increase the number of qubits and we'll increase the number of repetitions. So our circuit becomes both deeper and wider. So the way that we investigate that usually is that, no worries, it's an intimidating function, but the way that we investigate that usually is that we pick some Hamiltonian, either a global Hamiltonian, so z on all the qubits, or a local one, which means only z's on a subset, maybe 2 qubits out of the 100 that we have. And then we look at the variance of the gradient. So we'll pick one gradient, like we did in the very beginning, and we'll sample the gradient for many, many different points. So here for 100 different points. And then we look at at these values of the gradients and how they change when we increase the size of our circuit. Right, so this function is large, but what it does is given some number of qubits, so the wideness of the circuit and some repetitions, so the depth of our circuit, and a local or a global operator, so a z's on all qubits or just z terms on the first 2 qubits. It constructs this large circuit and evaluates the gradient for the top parameter 100 times and then returns us all these samples. If we now have that and we calculate the samples for 2 to 12 qubits with a linear depth, so for 4 qubits we have 4 repetitions, for 5 qubits we have 5 repetitions, and then we plot the variance. So here we plot the variance of the gradients in a semi-logarithmic scale. So on the x-axis you have a linear scale in the number of qubits, and on the y-axis you have the variance of the gradient in the logarithmic scale. Then we can see this is a straight line, a decreasing straight line. And a straight line in a semi-logarithmic plot means that this is an exponential decrease in the number of qubits. And here we also added a fit, so you can see that it really is exponential. And this is it's a result, but it's a very bad news for our circuits, because exponentially decreasing gradients means that we'll have a hard time to train and to optimize. Because if we don't have gradient information, how are we supposed to update our parameters? Since this is a very prominent problem especially for near-term devices, there are different ways or different ideas on how to mitigate these Barren plateaus. And one first question that you might have is, so I've moved the gradients, but does it also happen for natural gradients? And that's an excellent question, and that's left as an exercise to you. And then you can see what happens with natural gradients. Another idea that people had is, okay, so if I have a wide circuit with many qubits and a deep circuit, then I get Barren plateaus. What happens if I only have a wide circuit but not a deep circuit? So I constrain the depth of my circuit. Do I still have Barren plateaus? And with our function, we can just have a look at that. So we'll still vary the number of qubits from 2 to 12, but we'll fix the number of repetitions to only 1. And then we can sample the gradients and plot them again. And what we see is, again, we have this exponential decrease in the variance. So using short depth and z's on all the qubits will still give us the Barren plateaus. This is not the solution. Okay, other question. What happens if I don't use a global z operator, but I only use local z operations? So up to now, we used z's on all the qubits. What happens if I only use z's on maybe the first 2 qubits? We can do that again by saying, now we want a local operator and still depth 1 and a linear number of qubits. And if we plot that, then we can see that actually now, this is the red line, we can see that we don't have the Barren plateaus. So using a short depth or a fixed depth circuit in this case, with only 1 repetition, and a local operator will give us no Barren plateaus. Okay, now you might ask, this is a nice theoretical result, but if I use circuits with only one layer of depth, that's not really any good, right? I mean, that should be fairly easy to simulate. Does that still give me a quantum advantage? And maybe not, but there's knowledge of that local operators and short circuits give you no Barren plateaus. You can use that to construct larger circuits. And that's one way to mitigate Barren plateaus by so-called layer-wise training. So the basic idea is sketched here. So yes, you start with some circuit that might not give you a quantum advantage because it only has one layer of rotations. And this can also be efficiently simulated classically. You start out with that. But once you optimize this, you fix these parameters in the second step. So these theta zeros are already optimized in the first step, where we don't have Barren plateaus because we use local operators only and a short depth circuit. And now we add a second layer. So now we add a layer with, again, only a short depth, because this thing in the beginning is fixed. You can think of it as an initializing your qubits in some other state than zeros. And you optimize that. That will still give you no Barren plateaus because you still have a local operator and a short depth circuit. And then you can go on and on and on. And instead of optimizing all parameters at once, you linearly step through and optimize these to avoid Barren plateaus. We can implement that with Qiskit. So for that, we've now used we're now using 6 qubits. We're using a local operator, so not z's in all the qubits, but only the first 2 qubits. And for convenience, we'll define this function called minimize, which takes a circuit that we want to optimize and the optimizer. So this circuit will have only a few free parameters. Within this layer that we optimize, we choose a random initial point, and we'll define the expectation value that we are looking at and the gradient with respect to that. And then of course we shouldn't forget to map to the Pauli basis with the Pauli expectation converter and define a circuit sampler. And then we can define functions for the loss and for the gradient and call the optimizer. So in a nutshell, this function minimizes a given circuit. Now we just need to use that smartly. And one thing that will become very handy is that the ansatz circuits in Qiskit circuit library are mutable. What does it mean? That means that if I define my circuit as a real amplitude circuit with this, which is an ansatz circuit from the circuit library on 4 qubits with 1 repetition and a linear entanglement, it looks like that. But now, instead of redefining a new circuit, I can just say, okay, I changed my mind. I want 5 repetitions, not 1. And then you can set this attribute reps to 5 and the circuit will update itself. And you will see that the circuit now has 5 repetitions. And that's exactly the structure that we want, because we want to start out with 1 layer and then we want to increase these. So let's write a function for this layer-wise training. This layer-wise training now takes an ansatz where we can set the reps. It takes the maximum number of layers that we want to optimize and the optimizer, and will increasingly build up our optimal parameters. We'll start out with no optimal value. And now we'll iterate over different repetitions. We'll set the ansatz repetitions to whatever value we're currently at. We will bind the parameter values that we already know. So say we are in the 3rd iteration, then we want to fix all the previous optimal parameters, which we can do like that. And then we bind these to the circuit. So this is our partially bound circuit. If you remember, where many parameters are orange, so they're already fixed, but only the new ones, they're not optimized yet. And then we can call the minimize function with this partially bound circuit and optimize just this layer. Then we can, just to keep it, to see what happens in this optimization, we can print the current depth and the current best value. And then we append the optimal parameters that we just found to our global list. And if this idea works, then what we would expect to see is that we start out with short depth circuits and a larger function value. And as we increase the depth, as we increase the reps, and therefore the depth, then our function value decreases because we have more and more parameters and we cover more and more of the Hilbert space. Let's again use the amplitudes ansatz and gradient descent. Now I'm only using 50 iterations because I'm optimizing many times, so I'll just do a few steps every time. And then we can call this function. And here we can see that indeed we start off with a depth of 1 and have a value of 0.6. Note that we will want to go to -1. And then we increase the depth, and as we increase the depth, we optimize our function values. So this is exactly what we were expecting. And here we should not see any Barren plateaus, even if we increase the number of qubits. All right, so now we're almost at the top of the hour. So let's summarize what we've seen so far. The question that we were looking at in the beginning is, given a loss function that contains a quantum circuit that I want to train, how do I train this? The obvious answer would be to use a gradient descent technique. We've seen how we can compute these gradients using finite difference schemes, using analytic formulas, and we've seen how to do that in Qiskit. We noticed that using these gradients can be tricky if you don't know much about your loss function, and for instance, it's a very narrow loss function. But we've seen how to overcome that with natural gradients, and where by evaluating the quantum Fisher information, we are sensitive enough that we can update our parameters to the loss landscape. But we noticed that now that we solved this problem, we found a new problem, namely that these gradients are very expensive to evaluate, namely linear or quadratic in the number of parameters. And as a solution to that, we have looked at stochastic approximations, where we are trading off accuracy of the gradient for a cheap estimation of the gradient. And we've seen that since these are unbiased estimators of the gradients, on average, they will also converge to the correct minimum, and they will give us the same output. Now that we solved essentially all these technical problems of the gradients, we have looked at limits of training quantum circuits, and we have seen that variational circuits exhibit this feature of Barren plateaus, where the gradients vanish, or the gradients exponentially vanish if you increase the depth and the width of the circuit. But we've seen that if you use local operators and you train only layer-wise, if you train your circuits only layer-wise, that you can avoid these Barren plateaus and therefore still optimize your circuit. So I hope that this gives you a nice overview on how to train quantum circuits in many different settings. Remember that works for the VQEs, for QA, for arbitrary QNNs. And I hope that you've seen how to do that with Qiskit and that it's very straightforward to do. And I wish you a lot of fun with the remaining summer school and with training more circuits in your life. Goodbye.